Hi, we'll continue with volumes of solids. And here I have a right circular cylinder, which is a prism-like structure because the area of base remains, the cross-sectional area remains same throughout the length of the object. And we learned yesterday that area of base can be computed as volume of the cylinder can be computed as area of base multiplied by the height. So in this case, if this is the radius r, this is the height h, so we can compute volume is area of base, which is pi r square, because it has a circular base, and the height h. So volume of prism-like objects or prisms, even if you have a cuboid like this, you can pretty much compute the same way, area of base into height, which will give you length into breadth into height. So given this knowledge to calculate volume of prism-like structures, our next challenge is to find volume of pyramid-like structures. And what is a pyramid? It has a regular base, and at the other end you have a vertex. So you can, if you have a circular base, it's called a cone. Otherwise you can have a square pyramid or a pentagonal pyramid, hexagonal pyramid, like that, depending on the size of the base. So and today our challenge is to actually find the volume of the corresponding pyramid. So I have taken a right cone, and we know the area of the base, which is a circular base. So if this is the radius r, it will be pi r square, but it has a tapering cross section. So how do we compute volume of such things? So today I'm going to show you on a demo how actually there is a relationship between volume of a cylinder and volume of a cone. So for this relationship to exist, we have to take both objects of the same base and of the same height. And in that case, we'll learn about the volumes. So let me take you to the other camera. All right, here you see I have a cylinder which has a circular cross section and it has a height, and I have a corresponding cone which has almost the same cross section. You can see it this way, or I can put it like this, and you can see both of them fit almost identically. So the base is exactly same, the height is also same. Let me show you the height. I have a ruler here and I put it on top. They pretty much sits flat on the top, so they have exactly same height. Now I want to find the relationship between volume of these two objects. Let me do that. So what here I have some seeds here. I will put it in this cone and measure the volume, how many cones will fit in a given cylinder. So let's quickly do that. And since this is an experiment, it will have an experimental error, which is fine for us. So here I pour one full cone. Let me put one more and see if that fills. So I have put the second cone, and I think some more can go in. Let's try one more. So here is the volume, third cone, and within the experimental error, you see three full cones have filled the cylinder, and that is the relationship. That is, if you have a pyramidal structure, in this case a cone with exactly same cross section and same height, three of these cones will fill one of the cylinder. And that's how, if the volume of cylinder is pi r square h, the volume of cone will be 1/3 of the cylinder. So it will be 1/3 of pi r square h. And that is how the relationship happened. This relationship exists even when we change the pyramids. So let's take another example. I I have here a cuboid and corresponding pyramid. See, their base is exactly same, and you can check that. Their height is exactly same. So I will put the ruler again, and you can see it for yourself. See, yes. So that's there. And in this case, let's try and see if that works. So here I have a cutting in the cone, and I will exactly try to find out how many of these cones, the rectangular pyramids, will take to fill one cylinder, one cuboid. So in this case, here is one. And remember, these, because of the size of the seeds we are using and the packing factor, result will be slightly varying, but you will get approximately the idea. So that's 2. And you actually so in this case it has not actually filled up fully, but it will take 3 such cones exactly to fill up the equivalent rectangle, a cuboidal shape. So let me switch back the camera. So you saw there is a relationship of 3 times between the corresponding pyramidal structure and the prism, and that is what establishes, gives us a powerful tool to actually generalize this formula to other cases. Now I also want to show you, let me share my desktop screen, show you the relationship between other objects. So here, this is what we exactly saw. 3 times 3 of these. So volume of cylinder was 3 times volume of cone. If this radius is exactly same as this radius and this height is exactly same as this height. We also saw that true in case of a cuboidal. If you have the same base, then again the volume of cuboid is 3 times volume of pyramid. And this can be generalized to any other shapes. All right. So let me try to get back the okay, here I am. So in the last class, I asked you a question: which regular 3D object cannot have a net diagram? So I want you to think hard about this. We saw certain examples in the last class, and you go ahead and figure out which solid object cannot have a net diagram, and we shall discuss that in the next class. All right? See you. Thanks.